Dr. D. Sangeeta is currently a senior lecturer at the Department of Chemistry, Anna University, Chennai. She has completed her PhD in the field of polymer chemistry from the University of Madras in the year 2000 and has teaching and research experience of more than 10 years. Her research interests are in the following fields: fuel cells for clean energy, functional membranes for desalination, and polymers for biomedical applications. She has published more than 20 research articles in national and international journals and has more than 40 research articles in national and international proceedings. Presently, she is guiding 6 research scholars for their doctoral degree.
Welcome to the UGC lecture series for the subject of polymer science. We are doing with part 2 today. In part 1, we began with the unit 1 out of the 5 units which we discussed in an elaborate manner in the previous episode or part 1. As a continuation of what we have done in the part 1, that is, we got introduced to what is a monomer, what a polymer is, what is a polymerization, and how a monomer can be effectively forming a polymer. All these details to a little bit extent we have seen. As a continuation of this part, in today's part, that is part 2, we will be once again focusing on the basic concepts of polymer science, wherein we will be discussing about polymerization, a reaction, what is the difference between a structural unit and a constitutional repeat unit, what are oligomers, when do you call a polymer high polymer, what do you mean by degree of polymerization, and what is functionality and the importance of functionality for the different monomers. These things will be dealt in detail in today's part 2. Yes, we saw yesterday in the part 1 about what is polymerization. Polymerization is basically a chemical reaction where a monomer is converted into a polymer molecule, and this conversion happens in a suitable condition under the presence of a particular catalyst or an initiator, under a particular temperature and humidity and other ambient conditions or other operating conditions. A particular reaction will take place where there is a conversion of a low molecular weight monomer molecule into a polymer molecule. Here is an example for a polymerization reaction where styrene, which is called the monomer unit, is converted into polystyrene. So, what happens basically is you have the CH2 double bond CH with a phenyl ring substituted here is getting converted to a unit which contains a constitutional repeat unit of this particular structure. This is repeated n number of times. So, if I have n number of this monomer molecule, that is your styrene, they are converted into a polymer which is going to contain n repeating units of this monomeric unit called the constitutional repeating unit. So, this is your polymerization. Now, let us see what is structural unit and how is this going to be different from the constitutional repeat unit. The structural unit is referred as that particular portion of the monomer employed in the preparation of the polymer, and this is referred to as the structural unit. That particular portion of the monomer that is utilized for the polymerization reaction and which is available in the final polymer product is called structural unit. Then how this is going to be different from the constitutional repeat unit? Sometimes in certain monomers where you have homopolymers, both this constitutional repeat unit and structural unit remains the same, because it is one in the same monomer that is repeated n number of times and it is an addition type of polymerization. You have both of them as a same unit. But when the situation is going to be different, when do you have a different constitutional repeat unit and a structural unit? Yes, this happens when you have two different monomers condensing to form a new polymer, a new monomeric unit or a new structural unit that will be formed. That is going to be different from the basic monomeric units. How this is going to happen? Let us see with suitable examples. And this is the best example to show you how the constitutional repeat unit is different from the structural unit. Let me take this example. Here you have the monomer unit, namely the hexamethylene diamine NH2 CH2 6 times NH2. this particular molecule or the compound can behave as a monomer because of the very basic reason that it has two amine groups, NH2 on one side and another side also you have NH2. So, it is bifunctional in nature and hence it is eligible to behave as a monomeric unit. Now, this is monomer 1. There is one more monomeric unit in the formation of this particular polymer, and this second monomer is your adipic acid. Again, in this case of adipic acid, where you have COOH, CH2 4 times COOH. Once again, I have two carboxylic acid groups that are present on either side of this chain, that is either side of your methylene 4 times COOH and COOH. Again, this is also a monomer because of the reason that it has got bifunctionality due to the presence of two acid groups. Hence, these two monomers, let me say monomer 1 and monomer 2, both of them they combine to form a new polymer called polyhexamethylene adipamide. This is a classical example for condensation type of polymerization. In the earlier case, in the addition polymerization, there was only a simple addition of the same monomeric unit that was taking place, which led to the formation of the larger molecule or a polymer molecule. Now, here in this case, since I have two different monomers, monomer 1 HMDA and monomer 2 adipic acid, they condense with each other and then form a new constitutional repeat unit over here. Let me say this NH2 amine group combines or condenses with your acid group over here COOH to form a new linkage called amide linkage, that is nothing but your NHCO. Now, when such a combination or a condensation is taking place, there is an elimination product that is going to be your byproduct. Here in this case, it is H2O or the simple water molecule that goes out of the system. Now, what is going to be repeated in the polymer is going to be this particular feature, that is NH CH2 6 times. This NH2 and COOH have combined or condensed to form a new linkage called amide linkage, which is nothing but NHCO, and again the chain continues with CH2 4 times and CO, and hence it goes on. And at the end, after combining n number of such units, let me say n molecules of HMDA combines with n molecules of adipic acid to form a big polymer chain with this particular repeating unit, which is repeated n number of times with the end H and this side an hydroxyl group. Hence, now we can see this is your structural unit that is different from the constitutional repeat unit of your each monomer that are being utilized for the preparation of this particular polymer. And this polymer, the common name is polyhexamethylene adipamide, and the commercial name of this polymer is nylon 6,6, a very famous and an important polymer. Now, hence in this particular condition, one unit is coming from, that is one structural unit is coming from hexamethylene diamine monomer, which is your NHCH26 NH, this particular portion, and another unit, namely the second part, comes from the adipic acid monomer, which contains C double bond O, CH2 4 times and C double bond O. Hence, this becomes a classical example which makes you to understand how the structural unit is different from the constitutional repeat unit. Hence, in this example, the repeating unit in this particular example consists of two different structural units, and the constitutional repeat unit is a one which is repeated several times in the formation of the polymer. Now, going back to the earlier example, the first example, how this was different from the case what we have seen right now. Here, the structural unit and the repeat unit both remains the same. The structural unit is also CH to CH with a vinyl ring, and your constitutional repeat unit, that is a unit which is repeated n number of times to form the polymer, also remains the same. So, this is the basic difference between a homopolymer and a copolymer, where you have two different monomers condensing to form a new polymer chain. Now, let us move on to the next very important topic, that is functionality. How this is very important and what do you mean by functionality, and how this decides a particular compound to be a monomer which can be used to prepare the polymer. The functionality of a molecule is simply its interlinking capacity. It is the interlinking capacity of a particular molecule or the number of sites it possesses. That is, available for bonding with other molecules or other monomers under the specific polymerization conditions. So, when you have a particular condition for the polymerization to take place, a particular compound can behave as a monomer depending on their interlinking capacity, which is nothing but the number of sites that are available to form such links, and this is what is called functionality of a particular molecule. A molecule basically may be classified as monofunctional, bifunctional or polyfunctional depending on the number of functional units present in that particular compound. Now, depending on these number of binding sites available in the molecule, they are classified as monofunctional, bifunctional and polyfunctional molecules on whether it has 1, 2 or greater than 2 sites that are available for linking with other similar molecules. That is going to be your functionality of a molecule. Number of bonding sites, this can also be defined as the number of bonding sites available or present in a monomer molecule or any molecule for that matter. The generation of a polymer through the repetition of one or a few elementary units requires that the molecule must be at least bifunctional. Hence, for a particular unit to behave as a monomer in order to take part in the polymerization reaction to form a polymer, the minimum requirement is it should be bifunctional at least. Anything more than bifunctionality is also preferable because they have more bonding sites for developing the linkages to form a continuous polymer chain. So, the minimum requirement is bifunctionality. A minimum bifunctionality is definitely required for a compound to act as a monomer. Now, let us talk about this functionality features with several examples given over here. All these molecules which are mentioned here are different monomers, and how do they possess their functionality, and the functionality of such compounds are due to what? Let us see now with these examples. The first case, the example is ethene or ethylene you call it as, which is a basic monomer used to prepare the polyethylene. In this case, you have a double bond present between these two carbons. Hence, the bifunctionality is due to this double bond. Coming to the second case, propene, which forms the polypropylene or polypropene. Here once again the double bond functions or is responsible for the functionality or the bifunctionality of the molecule, and in this case it is vinyl chloride CH2 double bond CHCl. Again the unsaturation or the double bond is responsible for the functionality. Basically it is bifunctional. Now let us move on to other types of examples. For example, ethylene glycol is a very important monomeric unit. This molecule is also called as a monomer because of its bonding sites which are available in the form of hydroxyl groups, that is OH and OH. These functional groups that are present in these molecules can also be responsible for their functionality, and again in this molecule the bifunctionality is due to the presence of two hydroxyl groups, namely OH on one side and OH on the other side. Similar to this compound, you have adipic acid where you have COOH and COOH contributing towards the bifunctionality nature of this monomer, and in the case of hexamethylene diamine, it is going to be from the amine group, that is NH2 and NH2, that are once again present in this monomer, which gives the way for the molecule to behave as a monomer to form the polymer. Let us have a short break and then continue. Welcome back after the short break. Having seen what is functionality and its importance, now let us move on to another important term called degree of polymerization. What is degree of polymerization? This simply refers to the number of repeating units that are present in a polymer molecule. It refers to the number of repeating units that are available in a polymer. For example, let me say n number of ethylene monomer units combine to form a polymer called polyethylene, where the repeating unit is CH2CH2 and there are n number of such repeating units available in the polymer. Now, the degree of polymerization of this polymer is N, that is the total number of repeating units present in your molecule. N is called the degree of polymerization and is generally represented by d suffix p, dp. And in formula, how do we represent this dp? It can be written as dp is equal to molecular weight of the polymer divided by molecular weight of the monomer, because the molecular weight of the polymer is nothing but the total number of units present in the whole of the molecule, its molecular weight as a whole. When it is going to be divided by the molecular weight of the repeating unit or the individual monomeric unit, this will immediately give you the value of number of repeating units available in the polymer chain, which is nothing but your degree of polymerization. Hence, if we are known with the molecular weight of the polymer as well as the individual monomeric unit, it is possible to determine how lengthy the polymer chain is, or you can determine what is the number of repeating unit, which is nothing but degree of polymerization. Now, this same example we are taking over here, NCH2 double bond CH2 to form the polyethylene polymer with N repeating units. The subscript N in the above equation denotes the degree of polymerization, which is nothing but dp. It also indicates or specifies the length of the polymer molecule. It is indirectly telling you what is the chain length of the large polymer molecule that is formed during the polymerization. The degree of polymerization represents one way of quantifying the molecular length or the size of the polymer. This is because of the basic reason that greater the length, greater the number of monomeric units, greater is going to be the degree of polymerization or the N value. Greater the or lengthier the molecular chain, more monomeric units are available, and hence the molecular weight is also higher, and hence the size is also higher. So, all these are directly proportional to each other. dp is directly proportional to the number of units present, which is nothing but the dp, which is related to the chain length, which is again related to the size of the molecule, which is again related to the molecular weight of the polymer molecule. All of them increase when one point is going to increase. Now, there are two different words. One is called oligomers, the other one is high polymers. Generally, this is one way of classifying your polymers. We will be talking about the classification of polymers in various ways in the next part 3. Now, this is one particular way of classifying the polymers too. Why do you call, or when do you call a polymer as oligomer, or when do you call a polymer as a high polymer? Oligomers, they refer to the low molecular weight polymerization products such as that of dimers, trimers, tetramers, etc. All these low molecular weight substances or low molecular weight polymer molecules are referred as or called as oligomers. Oligomers refer to the low molecular weight species where the N value or the degree of polymerization value is lower. For example, something less than 1000 or 100, 200, then the chain length will be limited. You can calculate the molecular weight, which is also going to be a limited value, and the properties of the polymer when they are going to be in the low molecular weight form is also different from the same polymer molecule when there is going to be a higher molecular weight. Hence, such polymer molecules with low molecular weights, you term them as oligomers. Then what about the high polymer? Exactly, it is going to be the extreme on the other side of the polymer. When it is low molecular weight, you call it as oligomer, and when it is going to be very high molecular weight in the scale, that is very high scale or very high molecular weight, then you call it as higher polymers or high polymers. Hence, a polymer with molecules of high molecular weight, generally that is greater than 10,000, you call them as high polymers. So, these are the two differentiating words: low polymers, low molecular weight polymers, and high molecular weight polymers. Several examples can be quoted here. The same polyethylene, polypropylene, when they are going to be available in the low molecular weight form, or when they are available as oligomer, they will be sticky substances, but when they are taken for a higher molecular weight, they become more viscous, they become harder, they become a solid material. Hence, the properties of the polymer also is being decided by the molecular weight of the polymer. When it is going to be low, it is different. When it is going to be higher, the properties entirely change because of the increase in the chain length, size and the molecular weight of the substance. Now, let us take a beautiful example here to identify the different units, that is your monomer, your constitutional repeat unit, degree of polymerization and the molecular weight of the polymer too. Let us take the example of polyvinyl chloride, PVC it is shortly called as. This is the basic polymer whose structure, let me write it as CH2 CHCl 1000 times. Now, the monomer is vinyl chloride, which is nothing but CH2 double bond CHCl. Remember, whenever you write a polymer molecule, it should be written within a square bracket generally or a parenthesis like this, but this number should be mentioned. If a number is not possible, just put it as N or P or any alphabets, which tells you that it is repeated so many times and hence it is a polymer. And whenever you represent a monomer, it should definitely contain the functionality, minimum bifunctionality is required for a molecule, and that should also be represented whenever you draw the monomer unit. So, in this case, vinyl chloride CH2 double bond CHCl is the monomer. Coming to the constitutional repeat unit, let me say the unit which is repeated number of times in the polymer, which is nothing but CH2 CHCl is the constitutional repeat unit. The structural unit also remains the same here because it is an addition type of polymerization. Coming to degree of polymerization, which can also be written as N value, here the N value is 1000 and hence the value is 1000 here. And now the molecular weight of the monomer, how do we calculate? It is the monomer unit, that is a CH2 CHCl, you have 2 carbons, 3 hydrogen and 1 chlorine atom present in one monomeric unit. Hence, you just multiply the atomic weights of the carbon by 2 plus 1 into 3 for hydrogen and 35.5 into 1 for your chlorine. Simply add them to get the molecular weight of the monomer. Here in this case, monomer's molecular weight is 62.5. When we similarly calculate the molecular weight of the polymer, let me say the molecular weight of the monomer is known to us, which is calculated in the previous step, which is equal to 62.5, and now this number, when it is going to be multiplied by the N value or the degree of polymerization value, that is nothing but the number of units present in the whole of the polymer chain. When it is going to be multiplied, exactly it is going to give you the molecular weight of the whole polymer. Hence, the molecular weight of the polymer can be calculated by multiplying the dP value with the monomeric unit's molecular weight. Here in this case, it is 62.5 multiplied by 1000 to give you 62,500. That becomes the molecular weight of the polymer molecule. Now, as we have traveled through all this, what we have done in this part 2 is again a very basic information, fundamental concepts about the polymers we have studied. Polymers are basically large molecules that contains number of repeating units called monomers. Bifunctionality is the minimum qualification or the minimum requirement for any compound to become or to behave as a monomer. Polymerization is the process of conversion of a monomer into a polymer molecule, and dP, which is nothing but the degree of polymerization, represents the number of repeating units in a polymer molecule. So, as a summary, today we have done with polymerization, structural unit. How is this structural unit different from the constitutional repeat unit when you go for a copolymer or a triad polymer or a polyfunctional polymers, and what is functionality, and then finally we touched upon the degree of polymerization. Now, let me have some questions to test your knowledge. What is the difference between constitutional repeat unit and structural unit? What is the relation between degree of polymerization and the polymer molecular weight? The formula that relates the dP value with the molecular weight of the polymer, and then identify the monomer, the constitutional repeat unit, structural unit if it has, in the cases of these polymers, let me say PTFE, polytetrafluoroethylene, which is commercially called as Teflon polymer, PVC or polyvinyl chloride, another very important commercial polymer, and nylon 6,6, which comes from amine and acid groups. Now, the fourth question is, what is the molecular weight of polypropylene with the dP value of 3 into 10 power 6. Now, for calculating this particular molecular weight of the polypropylene, we know the basic monomeric unit structure of the propene. Put that structure, calculate the molecular weight of the monomer. You know what is the dP value, you have the formula. Now, you can calculate the polymer molecular weight too. Here is an exercise for you to practice. Give the structural formulae of the repeating units that would be obtained in the polymerization of the following monomers. Also, give the names of the polymers. Let us discuss the solution of this problem also. The first one is CH2 double bond CH COOH, CH2 double bond CH3 COO CH3, and here it is CH2 double bond CHO CO CH3, and this is your CH2 double bond CH3 and CH2 double bond CN. Let us analyze this and get the solution too for this particular problem. For example, this table identifies your different monomers which was given in the question, and you do have the repeating units placed over here to form the polymer, and the name of the polymer is given over here. In the first case, CH2 double bond CHCOOH, now you have bifunctionality due to this double bond. Of course, you do have a functional group here, but this is more active, and this is going to be the reason for the formation of a polymer. Hence, the repeating unit is going to be CH2, this double bond will be separated. This is going to be CH2 CHCOOH, and when this is going to be forming a polymer, the polymer is called polyacrylic acid. In the second case, it is CH2 double bond CCH3. Again, this double bond is active and is responsible for the polymerization reaction to happen. In this case, the repeat unit is going to look like this: CH2 CCH3, and this is going to be your substitution or the side groups that are available as C double bond OOCH3, and this becomes the main chain, this becomes the side chain. And this polymer is a very famous polymer called polymethyl methacrylate, shortly called as PMMA. It is also called as acrylates, it is also called as perspex. It is one of the most important transparent polymers. There are only very few transparent polymers that are available. For example, PMMA is a transparent polymer. You have polystyrene, and certain polyethylene polypropylene can also be made as a transparent polymer. Not many polymers are available in transparent form, and this particular perspex or polymethyl methacrylate is well known for its engineering applications because of very good strength in it, as well as it is transparent in nature. Another important engineering polymer which is also transparent is polycarbonate. Okay, now let us move on to the third molecule, that is CH2 double bond CHO CO CH3. Here again the double bond is separated, and this particular polymer you call it as polyvinyl acetate. So, this is your main chain, repeating unit, and this is your side group. Coming to the next example, CH2 double bond CH3 is a very simple molecule, your propene molecule, which forms CH2 CH3. CH3 is a side chain, and this is your main chain, and the polymer is polypropylene. Now, coming to the last one, that is CH2 double bond CHCN, which forms a repeating unit like this: CH2 CHCN. This becomes your main chain, and CN is your side group, and this is another very famous polymer called polyacrylonitrile. Hope you would have enjoyed this session. Let us talk more about the classification of polymers in part 3. Thank you.